All right, so we conclude this section by proving two additional theorems. So theorem number one is this. Let's suppose that the limit as n goes to infinity of a sequence Sn is infinity. And the limit as n goes to infinity of Tn is going to be some t, where t may be equal to infinity or finite positive number. Then the limit as n goes to infinity of Tn times Sn is going to be equal to infinity again. And to prove this again, we'll have to appeal to the definition of the limit. So what do we want to do? So let's write this as an idea first. What we want to do is the following. Given capital M greater than 0, I want to show that there exists an n in R such that if n is bigger than capital N, then my sequence, in this case Sn Tn, is going to be bigger than capital M. Okay, so I want Sn Tn to be bigger than capital M. How should I proceed? So what do we know? We know that Sn goes to some number. That number might be either a positive number or infinity. All right, so if I know this, then what we can do is the following. So we have two choices. Choice number one, limit as n goes to infinity of Tn is infinity. So if the limit of Tn is equal to infinity, then by definition of a limit, there exists, in this case it's an infinite limit, there exists a capital N in R such that if n exceeds capital N, it will follow that Tn is greater than 1. Right? Because for each capital M, definition of infinite limit is going to be satisfied. For each capital M, there exists a capital N that is positive. In particular, capital N should exist for m equal to 1. Let's call this N1. And number 2, because the limit, let's see, that's not the number 2, I'm sorry. So now also, since the limit of Sn is equal to infinity, then there exists capital N2 in R such that n bigger than n2, this would imply that Sn is greater than capital M, right? So for any capital M that I chose in the beginning, right, I should be able to find capital N2 such that if n is bigger than capital N2, Sn is bigger than M. That's just a definition of a fact, expression of a fact that the limit of Sn is equal to infinity. Okay, so if that is true, so then I'm going to set capital N to be the maximum of N1 and N2. Then in this case, if n is bigger than capital N, what do we have? We have that n is bigger than n1 and it's bigger than n2. The fact that it's bigger than n1 means then Tn is greater than 1. And the fact that n is bigger than n2 means that Sn is greater than M. But then, of course, this would imply that Sn Tn is going to be greater than product of 1 and M, which is equal to M. And so this part then is done, right? Because given any capital M greater than 0, I was able to find capital N such that if n is bigger than capital N, then the product of Sn Tm is bigger than M. And so that means that Sn Tn should go to infinity. So in fact, what we're doing here is already not just an idea, but a proof. So all right, so that is part 1. Now let's do part 2. So what is part 2? Part 1 limit is infinity. Part 2, the limit as n goes to infinity of Tn is equal to some t, and that t is a finite positive number. Right, because that should have been our assumption, right? So either infinity or a finite positive number. All right, so what can we do here? Again, I want to make Sn Tn bigger than capital M. How can I do that? What sort of things do I know about Tn? So I know that Tn converges to T. So because of that, the consequence of that is that for any epsilon there exists a capital N such that if n is bigger than capital N, then Tn minus T is less than epsilon. Well, so I'm going to select a specific choice of epsilon. I'm going to use epsilon equal to T over 2. So then, because for any epsilon, my definition of a limit ensures that there exists a capital N, so then there exists a capital N1 in R, such that n bigger than capital N1 would imply that Tn minus T is less than T over 2. Well, what does this mean? This is the same thing as saying n bigger than capital N1 would imply I can rewrite the inequality about Tn and T without using the absolute value sign. So I'm going to get minus T over 2 is less than Tn minus T less than T over 2. Let me just do something here. Implies. All right. But I can also add T to all three sides of this inequality, in which case, so T minus T over 2 is T over 2 less than Tn less than T plus T over 2, 3T over 2. Again, I added T to all three sides of this inequality. So the conclusion from this, so therefore, if n is bigger than n1, we have that Tn is going to be bigger than T over 2. All right, so T is a positive number. So I'm just ignoring the less than 3T over 2 business because it's not going to be useful to me here. Okay, now, because, again, the limit as n goes to infinity of Sn is infinity, by the definition of a limit, there exists infinite limit. There exists an n2 in R such that n bigger than n2 implies Sn is bigger than the number that I prescribed, and the number I'm going to prescribe is going to be m divided by T over 2, so this is 2m over T. Right, T is not equal to 0, T is a positive number, so I can divide by it, and this is not equal but greater. All right. So then, if we set n again to be the maximum of n1 and n2, whenever n is bigger than capital N, if it is bigger than capital N, then that means it is bigger than n1. And if it is bigger than n1, that means that Tn is bigger than T over 2. So we have that Tn is bigger than T over 2. And if n is bigger than capital N, then n is bigger than capital N too. So Sn is larger than 2m over T. And so then from here, we see that if n is bigger than capital N, then Sn Tn should be greater than T over 2 times 2m over T. 2's cancel out, T cancel out, and you get capital N. So for any capital M, I was able to figure out capital N such that whenever n is bigger than capital N, then Sn Tn is bigger than capital M. So that means that the limit must be infinity. So regardless of the situation, whether Sn goes to infinity Tn goes to infinity, or Tn goes to a positive number. In both cases, limit of Tn Sn ended up being plus infinity. All right, so that is a theorem one. Again, from point of view of just looking at this result, it is not surprising at all, right? Because if one sequence goes to infinity, another sequence goes to infinity, the product goes to infinity. If one sequence goes to infinity and another one goes to a finite number, their product still goes to infinity. But now we have been able to prove this rigorously based on the definitions that we produced in the beginning. And the final theorem of this section is going to be theorem number 2. Let's suppose that limit as n goes to infinity of Sn is equal to infinity. Then what can I say about the limit as n goes to infinity of 1 over Sn? That limit must be 0. That's number 1. And number 2, suppose that Sn is a positive sequence. So it's a sequence of positive numbers. Such that the limit n goes to infinity of Sn is equal to 0. So then, opposite to what we found in the part 1, then the limit n goes to infinity of 1 over Sn must be infinity. Okay, and let's prove this. So we need to prove both parts. Part number 1. So what do I know in part number 1? I know that the limit of Sn is infinity, right? And I want to work with 1 over Sn. So the fact that limit of 1 over Sn, limit of Sn is infinity means that I can make Sn larger than any prescribed number. And if I want to show that the limit of 1 over Sn is 0, I want to show that 1 over Sn can be made less than Sn minus 0. 1 over Sn minus 0 can be made less than any number. So what I'm going to do, I'm going to choose epsilon greater than 0, and I want to prove that the definition of this limit is going to be satisfied. So I choose epsilon greater than 0. Then, because the limit of Sn is equal to infinity, there exists a capital N in R such that, so how am I going to make Sn, 1 over Sn minus 0 less than epsilon? Or which is equivalent 1 over Sn less than epsilon. I can make 1 over Sn less than epsilon if I make Sn bigger than 1 over epsilon. Can I make Sn bigger than 1 over epsilon? Yes, because the limit of Sn is infinity. So there exists a capital N in R such that Sn is going to be greater than 1 over epsilon if n is bigger than capital N. All right, so if this is true, then again, what is 1 over Sn minus 0? That is absolute value of 1 over Sn. And because Sn goes to infinity, all Sns are positive. This is the same thing as 1 over Sn. And what do I know about 1 over Sn? I know that Sn is bigger than 1 over epsilon. So that means that 1 over Sn is going to be less than 1 over epsilon. Right? That is a consequence of this. But 1 over epsilon is epsilon. And so then the first part is done, because if I choose any epsilon greater than 0, going via the definition of the infinite limit, I end up with being able to find capital N such that this difference is less than epsilon, so that's it. Part 2, I have to be able to establish the same thing, but going backwards. So let's suppose that Sn is a positive sequence of positive numbers, rather. Of positive numbers such that the limit n goes to infinity of Sn is equal to 0. All right. I want to prove that the limit of 1 over Sn is positive infinity. To prove that the limit is positive infinity, I have to choose any capital M greater than 0. And I have to be able to show that 1 over Sn is bigger than capital M. But showing that 1 over Sn is bigger than capital M is the same thing as using the fact that Sn is less than 1 over M. Okay, so then I know that the limit of Sn is infinity is 0. So then there exists an n in R such that, let's see, Sn minus 0 is less than 1 over m if n is greater capital N. But Sn minus 0 less than 1 over m, what I know about Sn minus 0, of course, it's the same thing as Sn. And because Sn is positive for all n, so Sn is greater than 0, then absolute value of Sn is the same thing as Sn. So this means that Sn is less than 1 over m if n is bigger than capital N. But saying that actually is equivalent to also saying that 1 over Sn is bigger than m if n is greater than capital N. But that's exactly what I wanted to show, right? Given any capital M, I was able to find capital N such that 1 over Sn is bigger than m if n is bigger than n, and that means that the limit of 1 over Sn is infinite. Okay, and this concludes the section, I believe it's a section 9 on properties of limits, and we will continue the next section next time.